Okay, so let us continue from last lecture, right, and we will go ahead and do another problem. Like we said, a supersonic flow encountering a flat plate, okay, at an angle of attack. So let us see what we are going to get over here. Okay. Okay, so right. So this is my flat plate. And as we saw in the wedge from last time, okay, and with this flat plate as well, we are basically dealing with surfaces which have really straight surfaces. You know, this is like one straight surface. The wedge yesterday that we did, in the last lecture that we did, basically consisted of 3 straight surfaces, right? And we were able to use, you know, without too much of complications, we were able to find out coefficients of lift and drag, and, you know, talk about the properties in general, right? So if I have this, okay, and what we have here is essentially, so we have a free stream, okay. So let us say okay. Okay, this is a free stream. It's a supersonic free stream, right? This is making an angle of attack of alpha, right? We have this, let's call this as, say, A and B locations, right? A and B locations. So, so basically this is a flat plate, you know, it's got this slightly thick here. So we do have a pressure distribution on the top surface and the bottom surface, right? So let us kind of draw that, okay? So on the top surface, right, so on the top surface we will have a okay. So let's so this is the, you know, top surface pressure distribution, and on the same vein we will have the same on the bottom, okay. We'll have the same at the bottom. Okay. So essentially we basically have a, you know, a flat plate which is, you know, just a straight element, straight segment, okay. Free stream, supersonic, angle of attack alpha. This is the kind of pressure distribution on the top and bottom surfaces, okay. Now when this encounters, we have a supersonic speed when it encounters this flat plate, what do you think is going to happen? Okay. Now look at this corner, look at this look at this corner here at A, and look at the top surface. Look at the top surface. Okay. Now, if you look at this top surface over here, let me exaggerate that. Okay. Let me exaggerate the top surface. So, let us say this is the A at the top surface, right. So, therefore, here I have the free stream coming in, right. I am just going to draw a line for the top surface. Just look at this. We are looking at this particular surface out here, okay. This is just the top surface, okay. I am exaggerating this, okay. Okay. So I have a supersonic free stream, Okay. And at here, at the top surface here, this is the angle of attack which the flat plate is making with the free stream, right. So, what do you think is going to happen at this point? What does this point look like, right? So, from what we have learned so far, this is expanding over this corner. This is like an expansion corner here. So, what we would expect to see over here is an expansion fan, right. So, let me draw that. Okay. Let me draw that right here. Okay. So, let me say draw it this way. Okay. What we expect to see over here is an expansion fan. Okay. And if I were to draw the same thing over here, okay. So, this is the expansion fan, and the basically here if you remember right, the mu1 and mu2. So, this is, so let us in this, so now that we have an expansion fan over here, let us call this region as 1 and this region as 2. Okay. So, therefore, what I will do is call the Prandtl-Meyer function corresponding to this is mu1 and this as mu 2, right. We have that. Now, let us look at the bottom surface at A. Okay. So, if I look at the bottom surface at A over here, okay. So, what we can say is in this particular case, if you just look here, okay. So, flow is right. Flow is basically turned away from itself. So, this was the flow, it is turned away from itself, right. So, that gives us an expansion fan. Now, let us look at the bottom. Okay. If you look at that right over here itself, okay, this is the flow. Okay. Then because of this the flat plate here, the flow is turned into itself, isn't it? If you look at this, the flow is turned into itself. If you consider a free stream like that, okay, the flow is turned into itself. So, here what should that give us? It should give us a shock wave, right. So, what we will have at the bottom actually is a shock wave. Okay. We will actually have a shock wave over here. Okay. So, we will basically have a shock wave in here. So, let us call this region again as this region as the 3, which is behind the shock wave. So, this region is 1, right, which is the region in front of the entire flat plate, right. We have the free stream over here, and at the top surface it encounters this expansion fan up here. So, the region behind it, let us call that as region 2, and at the bottom surface we have a shock wave coming in. So, the region behind the shock wave is say region 3. Okay. So, let us do that. Okay. Now, again, okay. So, in here, okay, so in here, now that the flow has, is expanding over here, okay, flow is expanding over here. Now let us look at the trailing edge B. Okay, look at the location of the B. Now, the flow came in here. Now, let us see what will happen at the trailing edge. Okay, now the flow came in here. Okay, flow came in here. It expanded. Okay. Now, in here we at the trailing edge, okay, the flow still needs to merge with the free stream. Okay, the flow still needs to merge with the free stream, and when it comes over here, see, okay, the flow is moving along the say flat plate out here. Now it has to go along the free stream over here. You cannot allow it to expand anymore or move away from itself. Okay, so this sort of definition comes in handy when we when we're trying to understand this, in the sense that when it came at this corner, okay, it had a surface to sort of guide it along. So it came in here, okay, it expanded, but went along this surface. Okay. But now when you come, say, towards the end of it, okay, when you come towards the end B, okay, if you're still allowing it to expand it, we will not have it go along, we will not have it move smoothly away from B. It will not leave the edge B smoothly, and it will not join the free stream, and we don't want that. So in order that it follows the free stream smoothly at point B, so this will have to be shocked, so to speak. So basically we will turn the flow into itself, okay, so that it keeps following the free stream, right, and it when it leaves the top surface at the point B. So what we will have here now is a shock wave. Okay, so let me sort of write that here. B at the top, okay, flow is turned, so into itself. Flow is turned into itself, B at the top. So we again have a shock wave in here. So what we will have over here is a okay. Okay, so that if you now look at it, flow when it expands, okay, comes over here. Okay, now you shock this, so with this shock it deflects and keeps following. Okay, it doesn't come and expand over here and leave it like this. Okay, it comes here, it reaches the shock, and it deflects and keeps going according to the free stream. Okay, that is what the shock does. And on similar veins, if you look here, okay, if you look here, basically now when it gets shocked, it gets deflected, comes here, it would have gone this way. You don't want that at the bottom, right? You want it to go along the free stream, so you are going to expand it along this corner so that it follows the free stream. Okay, so therefore, so what we have at B bottom actually, okay, so B at the bottom, flow is turned away from itself. Okay, so we have an expansion fan, right? So we will have an expansion fan over here. Okay, so let me just sort of try to draw a free stream or something. So if you have, say, a streamline which comes like that, right? So it will move like this, and it will move along this. This will be my free stream. Okay, free stream values, it comes like this. Now when it comes over here, okay, so I have a free stream which is moving like that. Okay, now over the surface. Now if you look at this, isn't it? So this is how it is moving. Okay, now I would clearly, when it encounters the shock, what happens? It deflects and it starts moving this way. So there you go. So we have your free stream back, right? So similarly, when we come here, so say we have this here, right, and it deflects, so we get something like that. It comes over here. Now look at this, right? Had it continued, it would have gone that way. We don't want that. We want it to go along with the free stream. So it goes like that, and then basically follows the free stream, deflects and follows the free stream. Okay, fine. Well, okay. My artwork is a little out of place here, so okay. So there we go. Okay, a little better. Okay. So, there we go, and that is how it flows. Okay. So, now this is all. So, in a simple sort of very innocent sort of problem, we just have a free stream which is supersonic, and we have a flat plate with an angle of attack. We see a lot of interesting things going on here, right. So, okay. So, now let us go and find out basically the lift and drag coefficients for an angle of attack of 5 degrees, okay, and the Mach number 3, okay, for a Mach 3 flow. So, how are we going to do this? Okay. So, now that we know this, okay, let us proceed here. So, first things first. Okay. So, here the deflection here is what? Deflection here, if you see deflection here is, so basically Prandtl-Meyer function, from Prandtl-Meyer function we know that theta, right. So, this is my yeah, okay, yeah, same thing. So, from the Prandtl-Meyer function we know that mu 2 minus mu 1 is theta. Theta is the deflection, which in this case is our alpha, isn't it? So, this is known to us now, which is 5 degrees, right. So, now this is here. Okay. So, I can calculate mu 1 because I know Mach 1. So, in region. So, now m 1 is given to us as 3, okay, and theta is equal to 5 degrees. So, when we look up the tables, so from the Prandtl-Meyer function tables, okay, corresponding to m 1 equal to 1, m 1 equal to 3, we get mu 1, right, which is the Prandtl-Meyer function corresponding to Mach 3, right, corresponding to Mach 3, and we get that as 49 point. Okay. You should go and cross check this. You should go and cross check this and make sure I've got these numbers right. Okay. Okay. So, once we get that, so then we will calculate mu 2. Okay. Mu 2 is equal to mu 1 plus theta, right. So, this is theta is 5, right. So, once we do that, what we get here is, so, or 54.76 degrees. So, once we have that, again corresponding to this m 2, this mu 2, we can calculate the Mach number from the Prandtl-Meyer function tables, right. So, corresponding to this, okay, we get this from the tables to be 3.27. Okay. So, it is expanding. Okay. So, it is speeding up. Okay. So, this is given. So, we get these from tables, right. We get these from tables, new one, then we calculate this again, this we get. Now, we kind of go back and forth, back and forth. Here we knew the Mach number, we calculated the corresponding Prandtl-Meyer function. Here we knew the Prandtl-Meyer function, we found out the corresponding Mach number. So, we keep going back and forth. So, this is from the table. So, essentially what we see that what we have found out now is the Mach number in this region 3.27. Okay. So, let us write that here. Okay. So, we have the Mach number in this region to be 3.27, okay, and Mach 1 is 3. Okay. So, once we do that, okay, so now we can again find out from the isentropic tables. Okay. So, for now m 1, so let us find out. Now, for m 1 corresponding to this, again we get this from the isentropic tables, right. So, m 1 equal to 3, from tables we get P naught 1 by P 1, and I get that as nearly 37, and corresponding to Mach 2 equal to 3.27 from the same tables, right. We get P naught 2 by P 2 equal to 55. Okay, 55. Now, okay, so this is it. Okay, now P naught 1. Okay, the stagnation, the total pressures, they remain same. Okay, so P naught 1, since P naught 1 is equal to P naught 2, right. So, therefore, we can get a an value for P 2 by P 1. Okay. So, what we will get here is P 2 by P 1 is equal to, which is nearly 7. Okay. Now, all of this that we did, this is really, this is at, okay. So, all these calculations that we did. So, now what we have found out is so P 2 by P 1 is nearly 0.7. Okay. So, this is the relation between the pressures. Now, so this was the expansion fan. Okay. Now, let us go and look at the bottom surface. Okay. Now, at the bottom surface, okay, so now at the bottom surface, okay, so we have a incoming Mach number of 3. Okay. So, we have a theta, right, which is the deflection, which is 5 degrees, right, alpha angle of attack. So, this is also given. So, therefore, from the theta beta m relationship, we can find out the shock wave angle. So, from the theta beta m charts or plots or graphs, whatever you want to call it. So, corresponding to that, we get a beta which is 23.1 degrees. So, this is the shock wave angle. Okay. Let us go back in here. So, basically what we get here is the, okay, so this is the shock wave angle. This is 23.1. Okay. So, we get that here. So, now basically what we will do, like we did last time, we want to get a the pressure distribution, and hence we will be able to calculate the total force and the lift and drag, and hence their coefficients. Okay. So, let us look at the pressure changes in this particular case when the flow is going across the shock the bottom surface. Okay. So, here so now that we have an oblique shock here. So, then the the usual, so mn1. Okay. So, we can calculate that by m1 sin beta, right, that comes out to be 1.177. This is the normal component, this is the normal component of the shock across this, okay, the oblique shock. So, once we have that, okay, then corresponding to this again from the normal shock tables, okay, from normal shock tables, what we will get is the static pressure ratios, which in this case is P 3 by P 1, right. You remember this? So, this is where region 1. So, I am looking at pressures behind the shock and in front of the shock, this region is 3. So, we will call that as P 3 by P 1. Okay. So, and we get that as around 1.46. So, we have a P 3 by P 1. Okay. We have this. So, now let us go ahead. Now, that is all basically we need out here. Okay. So, we have an expression for P 2 by P 1 and P 3 by P 1. Okay. This is something that we have already learned, we have done it so many times. As long as you understand what the shock this flat plate is doing, basically expanding the flow here, shocking the flow here, shocking it back and expanding it back, we are basically through. Okay. So, now just to calculate the okay, let us look at this here. So, how exactly will we calculate the CL and CD? So, if you look at this, okay, although I think you should be aware by now, but anyway, okay, let me do this here. Okay, let me draw this here. So, this is my flat plate. Okay. So, this is my, sort of exaggerating that a little bit. Okay. Okay. So, this is my free stream and this is the alpha, right. So, in here, therefore, okay, so we have pressure distribution on the top, pressure distribution on the bottom, right. So, then we have this, say there is a resultant force, okay. So, these I take the components of the resultant force with basically this I mean in the direction of one is in the direction of the free stream, other is perpendicular to it. So, it is the free stream that we are taking as reference. Okay. So, then this becomes my drag and this becomes my lift. Okay. So, as you can see over here, so this angle is basically alpha. Okay. This is basically alpha. Okay. The way to look at that, the way to look at this is that this flat plate, okay, if it was like this, okay, then I would have my R vertically like that. Okay. Now, I turn it here. So, I turn the alpha this resultant vector by an angle alpha, which is the angle of attack. Okay. So, therefore, this whole thing transfers. So, then we still take the component of the force in the direction perpendicular to the free stream as lift and in the direction in this direction as drag. It will be okay. So, if I do that, okay, if I do this, so therefore, that is alpha, right. So, if you see from here, and I think this length, okay, we will denote this as C, which is this is the nomenclature which we normally use, the chord length or whatever. Okay. So, if you look at this, so lift now, okay, so lift out here is, so this was region 3, right, this was region 2. Okay. So, what is the total pressure? Total pressure difference is basically what? P 3 minus P 2. So, like we said, okay, if this was horizontal, then the entire lift would be just P 3 minus P 2, the pressure difference. Now, it is inclined. Okay. So, we want to take this. So, this becomes P 3 minus P 2 cos alpha and multiplied by the length. So, this is the total length. So, that is all there is to it. So, P 3 minus P 2 cos alpha, that is it. Okay. So, then CL and the drag of course is in the other direction, right. So, again P 3 minus P 2 sin alpha C, that is it. that is all. Okay. So, now again let us write this down. So, C L. Okay. So, if I were to write here, okay, let me write it over here now, or no, let me write it over here. Okay, now C L. Okay. Now, C L, therefore, now this becomes lift by, okay, this is the dynamic pressure. So, which if you remember, right, is half rho v square and all that. So, we wrote this differently, last lecture. So, just remembering that. So, the way we will write this is half gamma P 1 m 1 square by C. Okay, this. So, the bottom basically becomes this gamma P 1 m 1 square C, right. So, L, if you see over here, we will put this L out here, we will put P 3 minus P 1 here. So, what we get if we do this, okay. So, if I put this in over here, what we will get is 2 by gamma m 1 square P 3 by P 1 minus P 2 P 1 cos alpha, right. So, therefore, now we know m 1 given to us is 3, P 3 by P 1 and P 2 by P 1. P 3 by P 1 is what we have calculated, P 2 by P 1 is what we have calculated. So, we know these values, alpha is 5 degrees. So, we can calculate this, and what I get from here is around 0.12. So, coefficient of lift comes out to be 0.125. So, similarly, if you do the drag, okay. So, again C coefficient of drag comes out to be, okay, coefficient of drag. So, coefficient of drag is the same expression except this is sin alpha instead of cos alpha, right. So, that comes out to be, so which is a pretty good thing, because the coefficient of drag is not very much. So, that is it, okay. That is all we do. So, essentially, so this if we said this was our pressure P 2, this was our pressure P 3, okay. So, essentially, okay. So, if I had say pressure P 2 and P 3 here, so my entire resultant force would be what? Would be P 3 minus P 2 into C, which is this distance. Okay. Now, what I do is I incline this. Okay. I incline this. Okay. And I incline it by alpha. Okay. So, then what happens is, so this comes here. Okay. So, then this is still R, this is the same R, but we will need to take components like this. This is your lift, this is your drag. Okay. So, as you can see now, I rotate this whole thing. So, this becomes alpha. So, that is it. Okay. So, all we have basically done is used our knowledge of the expansion fan and oblique shocks, the how to calculate properties, etc. This is something which is not new. But what is interesting is how we are able to apply it somewhere here, okay, and calculate or study properties across surfaces, right, which again here are basically made up of straight elements. So, like we saw yesterday, so we had more than one surfaces, okay, attached to each other, and we were able to use you know, our knowledge of shocks and expansion fans, etc., to you know, calculate the lift coefficients of lift and drag across them as well. Okay, so this is like a simpler case when we have like one, you know, surface. Okay, let us you know, just look at, you know, one more small problem, and then we'll kind of sort of move on to other things. Okay, so so that's that. Okay, now instead of say something like this, okay, instead of something like this, okay, let me leave that in for a while. Okay, let me leave that in for a while, just to, you know, make a comparison. Okay, so let me leave that in. So like I said, we're basically talking about you know, talking about you know, surfaces which have several straight lines. Okay, so for example, let us look at this. Okay. Okay, trying to be this. Okay, this is basically a diamond shaped wedge. You can think of this like yesterday what we did was just the, you know, just this part. If you look at this, you know, just the top triangle, we did something like that, isn't it? But now we're looking at this as like a diamond wedge. Okay, so and of course we have a free stream coming over here. So this is my free stream. Okay. So again, if I have to calculate the coefficients of lift and pressure, we are looking at each surface. So we basically look at the pressure distribution there and take the net pressure force coming on resulting due to that. Okay. So now if you look at this, okay, if you look at this thing, what do you think is happening in here? So let us look at, say, let me call these, okay, that's okay, I am not calling it anything. Let us say here, let me call these surfaces, let me call these surfaces as say A, B, C, D, okay, and say this angle is epsilon, okay, and this entire length, okay, this length is say T. So this and this entire length is T. Okay. All right. So now if you look at the, now let's start looking at this wedge like we did here, right? For example, here we looked at the top part, we look at the bottom part, so on and so forth, we look at there, so on. We do the same thing here. Okay. So if you look here, okay, if it makes more sense, go and draw this separately and look at that. So if you do this, okay, so if you just look at this part, okay, let me just you know, draw up say this separately, this point out here. Okay, so I have the free stream coming in here, okay, and I have the surface, this surface coming in here. So what do you think is going to happen? The flow is being turned into itself. So we will have a shock wave, right? We will have a shock wave. So what we will do here is okay, right? Now what happens at the bottom? What happens at the bottom here? Same thing. Here too, the flow, if you look at this, the flow, if here, just look at a streamline. So if I have a streamline here, okay, flow is turned into itself. What happens to a streamline here? Same thing, it's turned into itself. So, we will have a shock wave at the bottom as well here. So, we will also have a shock wave at the bottom over here. Okay. There. Okay. Now, then what happens here? When the flow comes here, it gets deflected, and then it comes here, and then if you look at this place here, okay, what do you think is going to happen? We have this surface. Okay. So, the flow has there is a free stream, right. So, I have a free stream which comes here. Okay. It gets deflected, comes here. What do you think is happening over here? Okay. It should have gone that way. Okay. It should have gone that way, but what happens? It is turned away from itself, right. This surface is going away from itself here, isn't it? This surface is like that. So, it is like an expansion corner. So, what we will have there is an expansion fan, right. Makes sense? So, you can do this yourself, you know. Okay. That is it. So, essentially what is happening is that if you look at, if you extend say this surface, okay, this surface is being turned away from itself. So, therefore, we have a flow expansion over there, right. So, this is the deflection, this is the deflection angle over here, right. So, in here this happens. So, similarly over here too. Here also we have the same thing. Okay. The flow comes in here, it gets turned away from itself. So, again we will have the same thing over here. And so on and so forth. And again we will at the trailing edge, again we will use the same explanation that we did there, right, because now it has to join the free stream. Here it has expanded. So, it is moving this way, and you want it back in the free stream. So, you shock it. Okay. So, we will basically have again two shocks here, okay, so that it goes into the free stream. Okay. So, now our again job is, so if we have something like a wedge shaped something like this, how do we calculate the CL and CD? So, again let us call this region as 1. Okay. I will call this region as 2. Let me take that off. Okay. So, this region is 2 and this region is 3. So, essentially we will again have similar the way I have drawn the pressure distribution over here. So, I will also have the same thing on this surface and again the same thing on this surface, right. So, I think you know that by now. Okay. So, if I have to do this, so let me go ahead and sort of okay. So, let us see, let us do a problem where this all these stuff is given here. So, this epsilon is given to be say 15 degrees. Okay. Now, at a particular point here, the pressure is given to be 0.1 atmospheres. The pressure is given to be 1 atmospheres. Okay. And here suddenly we insert a pitot tube. We insert a pitot tube. Okay. Because of that, what will happen is there's a you insert it there. So, there will be a shock wave there. There is a normal shock actually here. So, if you have a normal shock here, okay, and so because the pitot tube is going to measure the static pressure, right. So, here the flow comes here, encounters this normal shock, and let us call this region as 4. Like which is just behind the normal shock, okay, and the reading of the pitot tube is given to be 2.596 atm. Okay. So, what we have to find out is this Mach number. This is not known. So, this free stream Mach number is something that we need to calculate, and this is the information that is given to us. Okay. So, how do we calculate this? Now, the pitot tube you know, the pitot tube will basically calculate the total pressure, isn't it? Total pressure behind the shock. So, which is the region which we have called as 4, right. So, this region is 4. So, what we are getting here, so this is actually nothing but total pressure, right, total pressure in the region 4, and this reading is nothing but the static pressure reading in region 3. So, this I can write, this is basically P3, isn't it? This is P3. So, what is given to us is essentially P naught 4 by P3, right, and this is given to us as, okay. Now, so therefore, now using this, right, using this we can calculate the corresponding Mach number from the tables. So, using this, the corresponding Mach number, Mach which is basically the incoming Mach number into the shock, isn't it, in region 3. So, this is the Mach number which we get as 4.45. Okay, you have to cross check this. Okay. So, so what we get from here, we will do a lot of this inverse. So, we kind of see we do not know anything here. We started from here the last time. Here we do not know anything other than this angle. So, and we know pressures etc. from here. We are almost kind of calculating it back. Okay. So, what we have got now is the Mach number behind the expansion wave. Now, this of course, this you will remember, this is mu1 and mu2, isn't it. So, corresponding to this Mach number, we can calculate the Prandtl-Meyer function of the right end of this expansion fan. So, again corresponding, so nu of M3, okay, we can get as basically nu 3, which is 71.27 degrees. Okay. So, therefore, again nu 3 minus nu 2 is the total deflection. So, if you look at this, so if you look at this here, okay, this angle is 15 and again this angle is also 15. So, this total deflection here between the two surfaces is 30 degrees. Okay. So, this is total deflection is 30 degrees. So, then this is 30 degrees. So, what we can calculate is mu 2, which is mu 3 minus 30, which is, so once we calculate mu 2, we can calculate the corresponding Mach number, isn't it. So, corresponding Mach number again M2 comes out to be 2.6. So, what we have calculated now is the Mach number here. So, M2 is 2.6. Okay, what we need to do is find out this incoming Mach number. Let us see what we have over here. Okay. So, let the shock wave angle be beta. Okay. Let the shock wave angle, okay, let the shock wave angle be beta. Okay. So, then okay, so M2 is this, right. So, now so we need this, okay, the normal component, which is equal to M2 sine of beta minus theta. Is that right? So, therefore, Mn2 is this is 2.6, okay, sine of beta I do not know and theta in this case is this. Now, if you look at this particular equation here, if you look at this particular equation, this is unknown, Mn2 I do not know and B2 also I do not know. How do I calculate this? Okay. Well, no simple way, this is just trial and error. What we will have to do is just do trial and error. Okay. So, I will just sort of give you one example of how we can do that. So, let us say like one case we can do. So, let m1 be 4. Okay. If m1 is 4, right, then theta is 15 degrees, right, we get a corresponding beta. We get a corresponding beta to be 27 degrees. Okay. Then we can calculate n1, right, which is m1 sin beta, and we get that as 1.816. Right. Corresponding to this, we get corresponding to this is from normal shock tables. Corresponding to this, we get an mn2, which we get to be here. mn2, I get this. Okay. Now, this is something, this is what I get from the tables, isn't it? Okay. But now, if you put this beta into this and calculate it from this relationship, okay, from this equation, then you get mn2 as 0.54. Okay. This is from equation above, the equation that we have written. So, that you can see that they do not match. Okay. So, we have to go and try one more. So, that is what I mean by trial and error. So, you have to go and, so next time say maybe try 4.5, m1 is 4.5 and see what you get. So, more or less when you kind of converge on a value which is not too off, then you are done. So, one possible solution, m1 is, so using this you can try, you can just try one more, you can try 4.5 and then 3.5 and see what you get. Okay. So, that is it. So, basically therefore, in this particular case we sort of came all the way back and were able to calculate the Mach number here. So, this free stream Mach number was 3.5. Okay. So, that sort of takes care of some problems that I wanted to do. What we will do now is trying to understand the 3D flow. Okay. Unlike we have done axisymmetric 3D, which is a quasi 2D, but we will try and understand what is the difference with a fully 3D flow. Okay. We will try to do that.